All right, so we're going to go ahead and get started. So I will share my screen. And today we are going to focus on three-dimensional geometry. And the first section is going to deal with planes. Before I forget, so today's schedule, we're going to do the norm. We'll lecture from 7:05 to 7:45-ish, take a 5-minute break, and then at the end we can play a Kahoot. Okay. So coplanar and non-coplanar. So any 3 points that are coplanar, so those 3 points basically exist on the same plane. For example, the 3 vertices of a triangle, this example should be up here, sorry. But the 3 vertices of a triangle are coplanar because they exist on the same plane. And non-coplanar points are a group of points that don't fall on the same plane. So for example, one point that is not in the plane of the triangle, or if you want to look at the quadrilateral, actually, that's not a good example because that's supposed to be, I think, a 3D shape. But imagine if you had a quadrilateral, if there was a point that was not on the quadrilateral, that would be a non-coplanar point. And knowing this, we know that 3 collinear points determine that a plane exists. So as long as there are 3 points that are collinear, which means that they fall on the same lines, then there is a plane. Okay, planes. When 2 planes intersect, what kind of figure is the intersection? So one way to imagine this is a wall meeting a floor where the wall and the floor are planes, and a line forms where the wall meets the floor. Similarly, 2 planes that intersect form a line. Is it possible for 2 planes to never meet? Similarly to how parallel lines will never meet, parallel planes will never meet. Can a line and a plane never intersect? We can build on the analogy that we previously used, and the intersection of the wall and the ceiling will never meet the floor. So similarly to that, a line and a plane will never meet each other. And skew lines are lines that are not on the same plane and do not intersect. And given any 2 lines that intersect, there's always a, let's just say not plane like that, but plane like P-L-A-N-E. There's always a plane that contains both lines. I will fix that. Okay. So I'll leave this up here for a few seconds to just go over the information, and then we can go ahead and move on to the next slide.
Can you put it up for about like 1 minute because I still need some time to read everything.
Okay. Okay, it has been approximately a minute, so I will move on to the next slide. Okay, so suppose line K intersects plane P at X, and we're going to, I don't know if I have a reference image for this. You can imagine, so let's say that there's a line and then there is plane P. I guess you can use this. Actually, I'm pretty sure this is the image that would go with, it could go, yeah. I think this is the image that would go with this example, but so then in this case, because line K is right here and plane P is right there, X would be O, which is right there, the intersection. If line K is perpendicular to every existing line in plane P that passes through point X, we can say that line K is perpendicular to the plane. Okay, so for example, line AE, referring to this image right here, line AE is perpendicular to ABCD. So you can see that it forms a 90-degree angle with the plane ABCD. Assume that plane P and plane Q intersect in line M, where O is a point on line M. Consider line J and line K in planes P and Q, so that each of J and K is perpendicular to line M at point O. The angle created between lines J and K is the angle between the planes. This angle is known as the dihedral angle. If the dihedral angle is 90 degrees, then the planes are perpendicular. So that was a lot of information, but to describe it in simpler terms, so if you were to look at line J and K, so that's going to be, this is theta, but this would be the dihedral angle, and if it's 90 degrees, then the planes will be perpendicular. So I'll leave this up here for a short amount of time, and then we can go on to the next slide. Okay, I will go ahead and actually move to the next section, which is 14.2, and we're going to talk about prisms. So a right rectangular prism is a 3D object. When I say 3D, I mean, I know like when you go to the movie theaters, you know what a 3D movie is. And 3D stands for three-dimensional. So I just put 3D there because three-dimensional that's longer to type, and abbreviations are kind of efficient and they're easier to use. So anyways, a 3D object, so a right rectangular prism is a 3D object with 6 faces, 12 edges, and 8 vertices. And face is each of the boundary polygons on the prism, and bases are top and bottom faces. So for example, so in this rectangular on the right, ABCD and EFGH would be the top, quote unquote, top and bottom faces, and then the rest of the 4 faces would be, they would be just called faces, but if you see the word base, that's referring to the top and bottom faces. And a polyhedron is a 3D shape with flat polygonal faces that should say straight, here, let me move down that image because it's covering a few words. It should say straight edges and sharp, there you go. Okay. Sorry, okay. A polyhedron is a 3D shape with flat polygonal faces, straight edges, and sharp corners or vertices. So an example of that would be this right rectangular prism, which is also a polyhedron because it satisfies all the conditions of a polyhedron. Okay. So next we have a prism, and or no, so that's like generally speaking. We're talking about regular prisms. This was a specific type of prism, but prism in general, it refers to a 3D solid figure with two congruent faces that are parallel, and with parallelograms as the rest of the faces. So remember, parallelograms are those are shapes that have where the edges, the four different edges are parallel, or there's two pairs of parallel lines or parallel segments. So it can be rectangle, square, and there can be, and then there's also, of course, parallelograms, where the specific type of parallelograms that you think about when you say the word parallelogram. But yeah, so that's basically what a prism is. And sides, we just went over this, or sorry, no, sides, I don't think we actually went over this yet, but there are faces that are not bases. That's basically right. The top and bottom faces are bases, and then the rest of the faces are sides. So right prism is a prism where all the sides are rectangles. And so, for example, this would be a right prism because all the faces are rectangles. And a face diagonal is a diagonal on a face. For example, this would be segment AC. And a space diagonal is a line connecting two vertices that are not on the same face. So for example, line AG would be a space diagonal. So it kind of looks like a 3D diagonal if you think about it, if you want to visualize it in that way. And dimension, so there's different dimensions of a prism because it's a three-dimensional figure. A two-dimensional figure is it's going to be quote unquote 2D, so it's going to be flat, so there's going to be two dimensions, but then for 3D there's going to be three. So if you look at the right prism, on the right, the dimensions would be AB, AD, and AE. Okay, so we have more examples of prisms. So on the left, we have a right regular pentagonal prism where the base is a regular pentagon and the segments connecting the bases are perpendicular to the bases. In the middle, we have a hexagonal prism where the bases are hexagons. And on the right, we have a prism that has parallelograms as its bases and sides. And this prism is also known as, actually, I'm pretty sure a parallel piped prism is the one in the middle. It shouldn't be on the right. Sorry about that. Yes, that was my fault. A parallel piped prism is the one in the middle where it's slanted. This one is not a parallel piped prism. I will go ahead and I can edit that after we're done with this slide. Anyways, if there's the word regular describing a prism, then it means that the base is a regular polygon. Okay, I'm going to edit this really quick. But I think the information so far presented is pretty straightforward because I mean we're just dealing with 3D figures, and I think all of you guys have at least come across volume maybe, and when it comes to volume you deal with 3D figures, so I feel like this is not too much of maybe new information. This is probably, there's maybe some stuff that you guys have not come across yet, maybe such as the parallel piped prisms, but generally speaking I think you guys have come across this before in the past. Okay.
I think, can I say something?
Yes.
I think how you judge whether or not, what type of 3D shape it is, all you need to look at is the bases.
Mm-hmm. Yes.
As long as you know how many sides are there, you can tell what type of prism it is.
Yeah. Yes, that's a good point. And I mean, there are different names, you know, for prisms, and generally speaking, I think you get them down because you just come across them, especially when you're learning about prisms. But they're like, you know, there's some prisms that might be a little bit more complicated, such as maybe like a 20-gon, a prism that has a 20-gon pentagon as a base. That's going to be a little bit, a unique prism, I should say. But generally speaking, I think the prisms that you come across, they're pretty easy to identify. But yeah. Okay, so next we're going to talk about volume and surface area. So we can measure the space that is inside of a 3D figure with volume. And the surface area is the area of all the surfaces of the prism that form the solid's borders. And the lateral surface area is the total area of the faces that are not bases. So we usually do not use lateral surface area, and we just refer to the total surface area as surface area. But the problems that we're going to be going over are going to be using lateral surface area. So in case you do come across lateral surface area, you'll know how to approach those types of problems. But I mean, at the same time, I think volume and surface area they're pretty, they're not the hardest topics to cover. So yeah, okay. So we have more information about volume, surface area, and space diagonal. So the 3 dimensions of a rectangular prism are often labeled as the length, L, the width, W, and the height, H. And the volume would be expressed as length times width times height, or L times W times H. And the surface area would be 2 times parentheses length times width plus width times height plus length times height, closing parentheses. And the space diagonal is going to be the square root of length squared plus width squared plus height squared. And additionally, the volume of a prism is equal to the area of a base times height. Okay, so a cube is a special rectangular prism where all of its dimensions are the same. And a cube that has the side length S has the following. So volume would be S cubed because you're just multiplying the same 3 lengths since we're dealing with squares. And a surface area is equal to 6 times S squared because we're just adding up all the areas of the volume and we're dealing with squares. And the space diagonal is going to be S times the square root of 3.
Excuse me, does the S equal square?
Does
the S in the problem mean square, or does that mean the height?
It's the side length.
Oh, side length.
Yeah.
Okay.
Yeah, because all of these side lengths in a square are equal to each other. Okay, and we can always come back to this slide and the previous slide before this to figure out problems. And speaking of problems, we are going to tackle our first problem. So, okay, consider cube STUVWXYZ. What is the area of SXYV if SV is equal to 4?
Could you go back to the cube exam? Could you go back to the cube notes?
This one?
Yes.
Okay.
So the space diagonal equals S. Is that times? Oh, s times the square root times 3.
Yes. Do you want me to go back to the problem now?
Yes.
Okay. Okay, I will go ahead and go over this problem. So what you would have first, what
I would like to volunteer to explain.
You want to what?
Explain the question.
Okay.
So like XXYV should be a rectangle. So its area is SX times XY. SX because SXT is a 45, 90 triangle. So SX equals 4 root 2 and XY is 4. So the area is 16 root 2.
Yes, that is the correct answer. Okay, so you just did my work there. So I'll just go over the side note. So the intersection where plane SXYV passes through the cube's vertices SX, Y, and V, this is known as a cross section. And we will deal with cross sections later, but it's when you can cut a 3D figure. You can cut it in half horizontally, vertically, or you can cut it like diagonally as shown in this 3D figure, but there are different ways to cut a 3D figure, I would say, but this is an example, but this is, yeah, so this would be a cross section, but in this case, yeah, the cross section would be a square. So you can start to keep an eye out for identifying different types of cross sections in different 3D figures because we're going to be dealing with them later. Okay, so for the next problem, the right regular hexagonal prism shown on the right has sides of length 4 on base A, B, C, D, E, F, and it also has a height of 8 units. So first we want to find the lateral surface area, and then we can work on each problem one at a time. But I think I formatted it so that 2 of the answers will pop up each in pairs. So maybe we can work on the problems in pairs. So go ahead and try to figure out 1 and 2 first, and then we can go over 3 and 4. But if you figure out 1 and 2, you can go ahead and work on 3 and 4.
Can you go back to the lateral surface area notes?
What does lateral surface area mean?
Lateral surface area it's the total area of the faces that are not bases. And remember, bases are the faces that are on the top and bottom.
So how do we calculate that?
So
that have to be said.
So the surface area, remember what the surface area is, it's just basically adding up all of the areas of each face. So then what you would do to calculate the lateral surface area is you would just subtract the area of the top and bottom bases. Or yeah, the faces, or yeah, bases. Okay, Okay, so I'll go ahead and go over the problem. Does anybody want to try to give a shot at the problem before we go over it? Okay, since I'm getting no answers, I'm just going to go over it. Okay, it should say, I just abbreviated the solutions, by the way, so there might be a lot of incorrect grammar, but that was on purpose, so that I could fit all the information on these slides. Okay, so there are 6 lateral faces, and each lateral face is going to be a 4 times 8 rectangle. So then what you would have done is 4 times 8, which is 32, and then you would multiply 32 by 6, and then you would get 192. And so, okay, that's lateral face area. Next, lateral surface area, sorry. Next we have the total surface area. And to find the total surface area, we must add the area of the 2 bases to the lateral surface area. So each base is a regular hexagon, and we can find the area of a regular hexagon that has a side length of 4 by splitting it up into 6 equilateral triangles. So the area of each base would be 6 times the 4 squared times the square root of 3 over 4. And remember, this is the formula that we got from equilateral triangle areas. And then if you recall from previous problems, we have dealt with finding the area of a regular hexagon, where we split up the hexagon into 6 different equilateral triangles. So in case you forgot about that, that was a refresher for 2 of those concepts. And if you simplify this, you would get 24 times square root of 3. And at the bottom, that should say surface, but the total surface area of the prism is 192, which was the lateral surface area, plus 2 times 24 times square root of 3, which is the area of the bases. So that would be your final answer. I'll leave this up here for a few seconds, and then we can go on to the next slide.
Is the next slide the answers to the...
Oh yeah, it is. Okay, so go ahead and attempt 3 and 4, and then we can go ahead and go over those problems too. So review and then attempt, and then we'll go over. Okay, I'll go ahead and go over the problems for number 3 and number 4. Okay, so 3 was pretty, I think it was on the simpler side compared to number 4. But for the volume, what you'd have done is you could find the area of the base, and then you multiplied it by the height. So then that would have been 8 times 24 times square root of 3, so that would have been 192 times the square root of 3. For number 4, so the original question was find AB, AC, and AD, and we're going to split it up into 3 different explanations. So for AB, AB, I guess I should say apostrophe, is a diagonal of rectangle AB v apostrophe A apostrophe. So AB apostrophe is equal to the square root of 4 squared plus 8 squared, which is equal to 4 times square root of 5. And AC apostrophe, for this one, you would consider the cross section AC, C apostrophe, A apostrophe. Notice that AC apostrophe is a diagonal of rectangle AC. Okay, I'm just gonna stop saying apostrophe. I think there is a term to say like AC apostrophe, but it's too much. Okay, ACCA. Since we know that CC is equal to 8, we just have to find AC. So then by drawing AC, we can form triangle ACD, which will end up being a 30, 60, 90 triangle. Now we have AC, which is going to be equal to CD times the square root of 3, which is equal to 4 times square root of 3. So AC would be equal to the square root of AC squared plus CC squared. And that's going to be equal to the square root of 48 plus 64. And if you simplify that, that would be 4 times the square root of 7. And finally, we have AD. So AD is a diagonal of rectangle ADDA. And to figure out the length of AD, remember how we have to split up a hexagon into 6 equilateral triangles, or we don't have to, but that's one way. So AD is equal to 2 times BC, and that would be 8. Therefore, AD is equal to the square root of 80 squared plus DD squared, and that's going to be equal to the square root of 64 plus 64. And just if you simplify that, that'll be 8 times the square root of 2. So that was a lot of information. Again, I'm going to leave this up here for a short amount of time, and then we can go to the next problem, or actually next section. Okay, I will go ahead and move on to the next section, and we're going to be talking about pyramids. So a pyramid is a polyhedron formed by connecting a polygonal base and a point called the apex. And so, for example, in this pyramid, point A is the apex because the base is B, C, D, E, and then there's point A kind of floating above the base. So non-base faces of a pyramid are triangles, and the lateral surface area of a pyramid, there should be the word area there, is equal to the sum of the areas of the triangles. Pretty straightforward. A pyramid is regular if its base is a regular polygon. And a regular pyramid is right if the base's center is the foot of the altitude extending from the apex to the base. So we're going to, I think I can display images too. But basically you can also have parallel piped pyramids too, where the point might, let's say for example, if point A was over here, then obviously it's not going to be floating right above the base. So then the height, or this imaginary line if you want to describe it, for example, AG, that's not going to be a 90-degree angle, so then that's not going to make it 90, or that's not going to make it a regular pyramid. Okay, so for right regular pyramids, slant height is the, I should say distance, not dance, from the apex to one of the base's sides. For example, AG is the height and AF is the slant height. So notice the difference there. Try not, just be careful when it comes to figuring out what the height is. Don't get confused with the regular height and the slant height. And the volume of a pyramid is 1/3 times the height times the area of the pyramid's base. And I will go ahead and fix dance to distance. Okay. And I'll leave this up here for some time so that you can absorb the information, and then we can go into the next slide, which is actually a problem.
So the volume of a pyramid is 1/3 of the volume. I'm sorry. I mean 1/3 of the volume of a normal polyhedron.
Oh wait, what's your, okay, so can you say like the whole question again?
I said, is the volume of a pyramid 1/3 of the volume of a regular polyhedron that has 2 bases?
I don't know if I would think of it in that way, because I mean the shapes are, you know, they're different. They obviously cover, depending on how big the shape is, it can cover more area, less area. So when it comes to the formulas of the different 3D figures, I would just go based off of what they give you. But I wouldn't try to like, I don't know if I would think, oh, the volume of this 3D figure is going to be 1/3, or for example, the volume of a pyramid is 1/3 of the volume of a regular prism, for example, like a rectangular prism. I mean, technically you are right, because like the only difference is at 1/3, but I don't know if that's an efficient way to think of the different volumes, because when it comes to dealing with different 3D figures, we're going to, I think, cover cylinders later, but they also have their own formulas. So just try not to get attached to that, oh, like this is 1/3 of the volume of a regular 3D figure or something like that. But yeah. Okay.
Also, is the
Yes.
volume of a sphere really hard?
I can't remember what it is at the top of my head. I don't think it's too complicated. You just have to plug in values. But I can't really remember it.
I googled it and it says V equals 4/3 pi r to the 3rd power.
Yeah. I think I'm pretty sure we're going to cover spheres. I'm not sure if we're going to cover it in this chapter, but we will eventually cover it. So yeah, I guess you can be ready when we cover sphere. I don't know. Okay. So it's 7:44. We can go ahead and take our break for 5 minutes, and then we can come back and figure out this problem. All right. Okay, so it's 7:49, so we can go ahead. Oh, was I displaying the answers? Oops. Okay. Anyways, we can go back to the problem. I accidentally displayed the answers, I guess, for the entire time. So hopefully you weren't tempted to look at them, but we can go over this problem, or you can try to attempt it first, and then we can go over this problem.
So the area is 1/3 times parentheses 36 times 5. I think, is that it?
Yes, I'm pretty sure.
Yeah.
Yeah. So that would be the area. Oh, sorry, no, volume. Sorry. Yes. So we got that. Let me see. Actually, hold on. Oh wait, yeah, so did you multiply AC in the volume, or did you multiply AO?
AC.
Ah, okay, sorry. Remember the height is, that's not, so the height is not going to be AC. The height is actually going to be AO. So if you can imagine in the 3D aspect, AC would be, that's going to be an edge of the 3D figure. AO is going to be the height. So you want to find AO to find volume. Okay, so I'll go ahead and go over the problem. So first, we're going to focus on finding the total surface area. And to find the total surface area, we would start by finding the area of the base, which is going to be BC squared, so that's 36. And then to find the height of one of the triangular faces, you would draw AO as seen in the picture, which is going to be the height of the pyramid. So because the pyramid is right, O is the center of BCDE, which is the base. So each triangular face is isosceles because the pyramid is right. And to prove this, we know that because AO is perpendicular to the base, it is perpendicular to OC and OD. And furthermore, OC is equal to OD, since O is the square center. So triangle AOC is congruent to triangle AOD by SA as congruence. So this means that AC is going to be equal to AD. So triangle ACD is isosceles, and the medium from A to CD, so A and then CD, is going to be the altitude. And because AC is equal to 5, and CM is going to be equal to CD divided by 2, which is 3, AM is going to be equal to 4, and these are all values that we figured out from triangle right triangle AMC. So that means that the area of ACD is going to be AN times CD divided by 2, which is the formula of a triangle, and that's going to be 12. So then the total surface area for 4 of these triangles plus the square, that's going to be 4 times 12 plus 36, which is 84. So that is how you would figure out the surface area of a right pyramid by finding the area of at least one of the faces, adding up the, or one of the triangular faces, and then adding those 4 up, and then the base. And then on the next slide, we have the solutions to finding the volume. Kessler, you were close, but we just needed to find AO instead of AC. So wait for a few seconds. I'll just display this up for just a short amount of time, and then we can go to the next slide. Okay, I will go ahead and go to the next slide. So to find the volume, what we would do is find the height of the pyramid AO, because we already know what the base is, or the area of the base is. So you can build a right triangle by connecting O to M over the base vertices. So if we go back to the image, we can see that we built our right triangle. And then in the figure, we have triangle AOM. And because OM is equal to BC divided by 2, which is 3. So if we go back, here's BC, and if we divide that by 2, that's going to be 3. And because we have, I'll just stay on the slide. And then we also know that AM is equal to 4. AO is going to be the square root of AM squared minus OM squared, Pythagorean theorem. So then that would be the square root of 7. So the area of the base is 36, and we just add, we multiply 36 times square root of 7, and then that's, you multiply that by 1/3, or you can divide it by 3, and that's going to be equal to 12 times the square root of 7. And was the explanation. I can leave this up here for a few seconds, and then we can go on to the next problem. Okay. So next, we want to figure out a formula for the lateral surface area of a right pyramid where the base is a regular n-gon with side length S, and where the slant height is L. So we haven't really, I don't know if we've done this before, but you can derive formulas based off of figuring out, just going through different steps and processes and eventually getting to the formula. Usually, I would say teachers just give you the formula, but I think maybe it's just a good idea to just go over this at least once, so that you can understand what it is like. Maybe to derive a formula. I did this, or I didn't derive formulas specifically for pyramids, but for other algebraic concepts in pre-calc. So, and I mean, it also kind of just depends on your teacher, but yeah, this is just good practice if you want to think about it in that aspect. Okay, I'll give you a few seconds left, and then we can go over the problem. Okay. So the lateral faces of the pyramid, that's going to be triangle, the width of the triangle times the height, L, and then base S. So each triangle is going to have the area, sorry, triangle W, sorry, it's just, it's an example. So each triangle has the area SL divided by 2. So that's going to be, base times height, which in this case is S times L. There's one triangle for each base's side, so there are n triangles that have a total area which is going to be equal to n times the area of one triangle, and you can just make that equal to NSL divided by 2. And NS is going to be equal to the perimeter of the base, because you're just going to be adding up the same number, whatever S is, n times based off of how many triangle faces there are. So then the lateral surface area of a regular pyramid is going to be 1/2 times the slant height times the perimeter of base. And remember, slant height is, for example, it's going to be L in this case. Okay, I'll go ahead and go to the next slide, which is about tetrahedrons. So this is a name for, the more common name for a triangular pyramid, and a regular tetrahedron is, it's where the edges, it's a tetrahedron where all the edges have the same length. Okay. So a regular tetrahedron has a sides of length equal to 6, and you want to find the volume.
I have a question. Why does it not look 3D?
Okay, I know it's kind of hard to imagine or figure out. So triangle BDC, that's going to be the base. AG is going to be the height. BAD is the back face. And then BAC is the face facing towards the left. And then ADC, triangle ADC is the face facing towards the right. So yeah.
Now I see it. Now I see it.
Yeah. Okay, I will go ahead and go over the problem. So, okay, so in order to find the volume, we need an altitude. So if you're drawing this out, you would draw AG. AG is perpendicular to plane BCD, so triangles AGB, AGC, and AGD are right triangles. AB, which is equal to AC, is also equal to AD, and AG is the same in all three triangles. So the triangles are all congruent by HL congruence, which is the hypotenuse select congruence. Therefore, BG is equal to CG, and that's also equal to DG, meaning that G is the circumcenter of triangle BCD, since it is equidistant from triangle BCD's vertices. If you forgot what circumcenter means, it's basically the center of the circle that you would draw that includes the 3 vertices of the triangle. So imagine if, for example, triangle BCD was inscribed in a circle, G would be the center of that circle. Okay, so triangle BCD is an equilateral triangle, therefore G is also triangle BCD's centroid. Centroid is a little bit more complicated to explain, but I will show an image of it because I don't know, I think it's better to see an image of it. Okay. Looking at BG, triangle BCD is equilateral, so segment BM is a median and an altitude. Hence, DM is equal to DC divided by 2, and that's going to be 6 divided by 2, which is 3. And BM is equal to 3 times the square root of 3, and that's a 30, 60, 90 triangle BMD. Because a triangle centroid divides its medians in a 2-to-1 ratio, BG is equal to 2/3 of BM, which is equal to 2 times the square root of 3. And we can then find AG from right triangle AGB. So AG would be equal to the square root of AB squared minus BG squared, Pythagorean theorem, which is the square root of 36 minus 12. And that, if you simplify that, it would be 2 times the square root of 6. So the area of triangle BCD is DC times BM divided by 2, which is 9 square root of 3. So volume is equal to the area of BCD times AG divided by 3. And that would be 18 times the square root of 2. Okay, I'm going to start this lecture really quick. I'll just pull up an image. So this would be centroid, I think. So if you just look at the images, I think you get a better understanding of it. We did go, I'm pretty sure we went over centroids in a previous lesson chapter, but it's just kind of harder to explain, I guess. But as you can see, so the midpoints of the triangle are all connecting to the centroid. So then, because these are midpoints, that means that the sides that the midpoint is dividing, the sides that the midpoint are dividing they're going to be equal to each other. But you can see that there are different sets of equal sides. So yeah, that's what a centroid is. Let's see if I can get back to the presentation. Okay, no. Okay.
When are we going to do a Kahoot?
We will do a Kahoot soon. I would say less than 10 minutes, maybe 5 minutes. Or let's see. This last section we have 2 information slides to go over, and then we have 2 problems. We can go ahead and go over the 2 information slides, and then I think we can say
I have a question. Shouldn't be there an N at the end of polyhedron?
Oh, this is a plural, polyhedra.
Oh, regular polyhedra.
Yep.
Okay.
Okay, but yeah, we can play Kahoot after we go to these two slides. So a regular polyhedron is highly symmetrical, being all of edge transitive, vertex transitive, and face transitive. So for example, there'll be regular tetrahedron and a cube. So the faces are all equal length. The vertexes are all going to be equal measurements, or the angles, and then the edges will all be the same, or yeah, so everything is going to be equal to each other. So that's what a regular polyhedron is. It's like a regular polygon, but it's you apply 3D characteristics to it. So there are 5 different types of regular polyhedra. They are described below. So there is a tetrahedron, which is what we just went over. The face type is a triangle, and it has 4 faces, 6 edges, and 4 vertices. A cube is, and it has a square as its face type, and there's 6 faces, 12 edges, and 8 vertices. An octahedron is a triangle. It has 8 faces, 12 edges, and 6 vertices. A dodecahedron is a pentagon, or the face type is a pentagon. It has 12 faces, 30 edges, and 20 vertices. And an icosahedron is the face type is a triangle, has 20 faces, 30 edges, and 12 vertices. And these regular polyhedra are known as Platonic solids. I don't know. Let's see if I can pull up an image of an icosahedron, because I mean, you can just imagine. Yeah, so this is a pretty good example of what an icosahedron. So you can see it has a lot of sides, and it doesn't, I mean, it sort of has the same structures of a soccer ball, but it's not. It doesn't at the same time. So
Is there any Latin or Greek pro or suffixes involved with it?
well, like the different polygons that we've been studying, there's like it ends with like gon, hexagon or pentagon, or it just ends. Let's see. Whoops. Here we go. But if you noticed, I guess the polygons that we've dealt with, for example, oh wait, no, I'm talking about polygons. No, sorry, we're talking about 3D figures. So I think I'm not exactly too sure, but if you've noticed a pattern, the words end in dron. So I think, or yeah, he drawn. So I'm pretty sure that has some meaning to it. And then, like, for example, tetra, octa, dode, icosa, or those are all, I don't know if it's Greek or Latin, but those are roots. So yes, I'm pretty sure there are Greek/Latin roots and suffixes that come into play with these different shapes. Okay, so it's 8:13. I think we can go ahead and play a Kahoot. I think this one's on the longer side, so we can go ahead and
Can we go overtime, please?
overtime. There's, I think, wait. Let's see. Because I think this one is pretty long. There's 18 questions. I don't know if we're gonna go overtime, but we might finish a few minutes before class ends, or if not, class ends, or maybe we might actually go overtime. But since we were talking about volume, we haven't necessarily learned cones, cylinders, and spheres yet. So we can go ahead and do this one because we were just talking about prisms. Okay. The music. Oh, they have different music. Gatling P2.
Gatling P2000 shall destroy you all.
There's nobody else. There has to be.
Am I the only person joining?
What about Alvin? Or okay, yeah.
Alvin Chipmunk.
No, I didn't log in yet.
Oh,
No, hey, that's an imposter.
Yeah, that's an imposter.
okay.
So we have Elika. We have this Adam imposter. We have this Alvin imposter. Oh, and we have them Citron.
2010.
2010. Why 2010? 2000.
Because I am superior to you.
Who said just because you have a bigger number means you're... And besides, galaxies...
Okay, because Citron is superior to Gatling Peas.
No, you are not. Gatling
Citron are the best. Citrons are the best.
Nice.
Yeah, Gatling P2000 is better than Citron.
It's called a citron.
Okay, cube. So you would have done 1/2 cubed. So that would be 1/2 times 1/2 times 1/2. So that's going to be 1/8. So that's how you'd have gotten it.
Thank you. Thank you. Take that.
What is the best approximation for the volume and cubic units of the box?
Citrons are always superior, or if citrons are always superior to Gatling peas. I shall prove that citrons are better than Gatling peas.
First of all, Gatling peas are one of the oldest plants in the Plants vs. Zombies universe. Second of all,
citrons are from the future, so they are super high tech plants. Okay, citrons are from the future. What? Okay, so they're superior because they're from the future. You know. Great.
Wow, who gets 378 cubic units?
So that would be
My mouse slipped.
Your mouse slipped. Yeah,
But
definitely.
I can still prove you wrong. Because I'm still first.
I ain't giving it nothing.
I don't think you should use deep.
You
I don't think this
should,
question.
you should do like Paul.
I don't think deep is a good way of expressing it.
I don't think so either, actually, because I just found this Kahoot on Kahoot. So I was like, oh, we should play this, and then nope. I guess we could. I mean, it's fine, but the use of words to describe.
Like, actually, I use it, I depend on like the new denominator. Like you see, the denominator is 2 and then you times 4, so I just chose 8, but I think it's wrong. Because you can like reduce fractions. So I don't know. Just gonna bite my teeth and hope I'm right. And I got it wrong.
Yes.
Bye. I'm still superior to the Gatling Pea.
Hey, at least I'm still having a steady streak.
Who cares? Who cares if we have a streak? I'll just start my streak once again. And I am still superior to Gatling
Alex is on a streak.
The edge length of each small cube is 2/3 inch. What is the volume of the? What do you mean? Where's the picture?
Hey, you don't need a picture to solve this, you know?
I know. I'm just asking.
And
Wow, nobody got it right.
So
that makes no sense.
I think I know what we got wrong.
you would have multiplied
I don't.
2/3 3 times. So it would have been 2/3 times 2/3 times 2/3, and that would have been 8/27.
So apparently, do we have to like go like sue the question, like sue the person?
Here, let's
Lawsuits. You get money.
Sue. We want to sue.
Okay, so
Everybody gets a portion of it. Don't worry. Once we get the lawsuit all done, we will make sure everybody gets a small portion of it. Everybody gets equal
the
amount.
question was saying that one side length of the cube was 2/3 of an inch. So you'd have just done 2/3 times 2/3 to find the area of the base, and then you would have multiplied it by the height, which was 2/3, because you're dealing with a cube, so all the edges are going to be equal. So then you would have gotten 8/27.
Apparently, you have a lot of streaks, so I can start again.
I will still beat you, Citron.
It's pronounced citron.
Citron.
Citron. I believe the citron will not lose to a Gatling Pea. Whoever, hey, stop singing.
Who says I need to stop?
Sure, then continue. I'll need computer audio.
Nice.
Wow, everybody got it right. I'm still behind you for some reason. Six inches times 5/3. So it's 105. So it has to be 10.5. What's 10.5? Oh yeah.
Oh my god.
Yes, the galaxy has risen. All right, so let's see who won. Yeah, Galaxy 2000. Okay, Alvin Chipmunk, the imposter, and on top we have Elika.
Good job. All
Wait,
right.
who are the runner-ups? I want to see the runner-ups.
Let's see if I can.
So Alvin, I'm going to say this, and I'm going to rub it in. Oh dang it! I better than you.
Okay. We have 4 minutes left, so we can do this last problem, and then we can call it a day. All right. So ABCDEF is a regular octahedron where AB is equal to 4, and we want to find BD, AF, the area of BCDE, and the volume of ABCEF. Okay, I will go ahead and go over this problem. So BCDE is a square. So I'll toggle back between the slides. But BD is going to be equal to BC times the square root of 2, right there. And then as I was saying, yeah, so BD is going to be BC times the square root of 2 because it's going to be a 45, 90 degree angle that's going to be formed if you draw BD. There's going to be 2 of those triangles. So irregular polygon sides have the same length. So BC is going to be equal to AB, and that's going to be 4, and BD is going to be equal to 4 times the square root of 2. Next, we need to find AF. So rather than thinking of the octahedron as square pyramids, A, B, C, D, and F, B, C, D, E attached together, we can think of them, or we can think of it as B, A, E, F, C, and D, A, E, F, C stuck together. So that means that A, C, F, E is going to be a square. So AF is going to be equal to BD, and that's going to be 4 times the square root of 2. BCDE is going to be, this is number 3. But BCDE is going to be a square with a side length 4, so then that's 4 squared, which is equal to 16. And then finally, to find the volume of ABCEF, we want to think of it as 2 congruent square pyramids, ABCDE and FBCDE. And to continue on with the process of finding the volume of the regular octahedron, because the altitudes from A and F of the 2 pyramids make up AF, the height of each pyramid is AF divided by 2, which is 4 times the square root of 2 divided by 2, which is equal to 2 times the square root of 2. So the area of a base is 4 squared, which is 16. So the volume of each pyramid is going to be 16 times 2 square root of 2 divided by 3, which is 32 times the square root of 2 divided by 3. So that means that the octahedron is going to have the volume 2 times 32 square root of 2 divided by 3, or 64 times square root of 2 divided by 3. So here is a rundown of the explanation, and I'll give you guys some time to review over it, and then once we're done with that, we can call it a day.
The easiest out of all of these questions is find the area of BCDE. This is true because all it is a square, and we already know a side length. The side lengths, so we can easily tell what it is.
Yeah. Okay. All right. So that was class for today. I've seen the chat again. Thank you guys for coming today, and next class we're going to be focusing, or I can't remember exactly what it is, but we'll be starting chapter 15. And yeah, I hope you guys have a nice day. So bye. See you next class.
Bye.